is my pleasure to announce now for this last session of this long day, where we will have 3 additional talks, to announce first Dominique Greneche, as he puts himself, ex-CEA, but mainly I think your own boss. It's much better, of your own company. And the talk is the Thorium cycle, past achievements and future prospects. So please go ahead and let's see if this mic
Thank you very much, Mr. Chairman. So I am happy for 2 things. First, to see so many people here at that time. I expected, 1 or 2 people, me and just the chairman, but fortunately you're at least, well, so many people. So thank you very much. And the second thing is that many things which are on my slides have been said already by myself since 30 years and by many other speakers. Is the mic working? Can you hear me?
Let's see.
Apparently, yes. So I said that many things have been already said, including by Professor Carlo Rubbia. Please have a seat. Thank you. And but with some things, I disagree. So we will open the question and the discussion for that. So you saw already many times a slide. I don't know why, but you see at least 3 or 4 times. Well, this is the main headlines of my presentation today. I will not go in details in each of these points, once again, because many things have been said, and I don't want to lose my time by repeating, once again, what has been said before. General consideration, why, you know why thorium. But maybe you don't know yet that the use of thorium was considered since the very beginning of nuclear energy. I am writing a book, in fact, on nuclear reactor history, and I discovered that there was a new pile committee established in 1944, April. I have the report of this by Enrico Fermi and so on, with 2 Nobel Prizes, Eugene Wigner, 3 Nobel Prizes, Enrico Fermi and James Franck. And it was said, written, that more work should be done on nuclear development of thorium 70 years ago, a little bit more. So this committee also suggested experiment to develop reactors that would convert thorium to uranium-233. Then it was said several times there is a long story of thorium. There was first a symposium or a conference. The first one was in 1962. Unfortunately, I have not the proceedings, but I have the proceedings of the second one, which was held in Gatlinburg in 1966. It was written, "It is time to take a fresh look at the reason for working on the thorium fuel cycle and its long-range prospects." Okay. Myself, I made my PhD 40 years ago with Jules Horowitz on thorium. It was at Saclay, 73, exactly 40 years ago. It was in November, a high-temperature reactor. So thorium is not, as you can understand, a new story. It is a very old story. Why thorium? You know this quite well, so I just skip this one. Thorium gives uranium-233. Fission gives energy. I can stop here. Well, it's a little bit more complicated. It has been said many times, the important factor to characterize the interest of thorium is the eta factor, which is the number of neutrons you recover when 1 neutron is absorbed in the fissile nucleus. So let's compare the properties of uranium-233 compared to uranium-235 when you have neutrons going in the fissile nucleus like uranium-233. It absorbs the neutrons, and in 8% of the cases, it doesn't fission. For uranium-235, it's 15% of the cases. Now it fissions in 92% of the cases, and only 85% for uranium-235. You see here that uranium-233 is better than uranium-235. And this is characterized by what we call the eta factor, which is, once again, the number of neutrons you obtain when one neutron is absorbed in the fissile nucleus. It's 2.3, about 2.3 for uranium-233, and hardly greater than 2, 208, 207 for uranium-235. This is a big difference. So here again are the value of eta for the main fissile isotopes, and from now you can see that uranium-233 is the best fissile isotope in thermal range, and the best one for fast neutron is plutonium. All the history, I would say, of nuclear reactor is here. I mean, of the fast breeder reactor. It's behind these figures. This explains why, partly, why the plutonium is the best fissile isotope, once again, for fast breeder reactor. Well, uranium-233 is not so bad, but less good than plutonium. You can breed only if eta is greater than 2. 1 neutron to sustain the reaction chain, and the other one to make a new fissile isotope. So you need to have eta at least equal to 2. It is as simple as this. So the difference for uranium-235, the difference with 2 is very low, only 0.07. And here the difference is 0.3. This makes, once again, a big difference. And this is the reason why you can imagine, and it was done, breeding in thermal breeder reactor, which is almost, which is impossible with uranium-235, and which is possible with uranium-233. Okay, but thorium is not a substitute to natural uranium. Thorium is not a substitute to natural uranium. One can sustain a reaction chain with natural uranium. With thorium, we cannot. In other words, if uranium had not existed on the Earth, probably we would not be here. Only thorium would not be here, almost. Thorium occurrence in nature has been discussed several times here, but let me say, sorry to be a little bit provocative, thorium reserves is not the problem. This is not the problem. Why? Because I say, Professor Rubia this morning was 1 ton of uranium, of thorium, well, let me explain this. Remind these figures, only one figure to remind. To make 1 gigawatt electric during 1 year, you need 1 ton of fission. To make 1 gigawatt electric during 1 year, you need 1 ton of fission. 1 ton of fission. So if you transform, let's say, 1 million tons of thorium into uranium-233, and if you fission it, you have 1 million gigawatt electric years. So you have nuclear energy for thousands of years. That's true. This is not, a ridiculous idea. That's true. So, once again, whatever the thorium, million tons is sufficient anyway to sustain nuclear energy with thorium, provided that, of course, you transform it to uranium-233 and you fission it. The same thing for uranium, by the way. Well, I skip on this one just to, there are 4 possibilities to use thorium. 4, not 3, not 5, 4. First is use uranium-235. Thorium has been used in the past. I remember I worked at General Atomic Company in California at that time, and the basic thorium cycle was based on high-enriched uranium. It was said in some of the slides, 93%. Suddenly, Jimmy Carter, president, arrived on power and said, well, no more high-enriched uranium in reactor. It's a very preferred. General Atomic was in a bad situation at that time. They said, well, what we are going to invent? And they said, well, we are going to invent low-enriched uranium, medium-enriched uranium, which is 20% uranium, which is a mixture of thorium and MAU cycle, and mid-enriched. It's possible to do this. I made a lot of study myself on this, but, well, we can discuss. Not very attractive. Second is to use uranium-233, which is the best, which is a nirvana, you know. But you must have it first. You have to produce it. And the fourth solution is to mix it with plutonium. I think this is the only way immediately in the next 10 years to start a thorium cycle. Well, this is the boss. This has been said several times. The pioneers, the high-temperature reactor. Thorium has been used at least 15 reactors. The list was given several times, so I skipped this one. The results also have been, there have been, you know, tons and tons of that thick studies on thorium in the past, so I will skip this one. I prefer to take time to discuss particular point. So, breeding condition can be achieved, at least on the paper. It has been done at the shipping port, the reactor, this was mentioned, but with complicated system, which would be difficult to extrapolate to commercial reactors. On the paper, it's possible, once again. But what you can achieve is what we call near breeder reactor, which is a reactor with a conversion ratio close to 1, 0.9, 0.95. And from this start, it's already very interesting to have implement thorium. For fast breeder, it's questionable. You can discuss this. But the physics say that, unfortunately, thorium cross-section for normal fast breeder reactor is 3 times less than the one of uranium-233, and than uranium-238. And, well, uranium-233 has not outstanding properties. So fast breeder reactor with thorium is, well, I mean, not so interesting compared to uranium-plutonium cycle, except putting thorium on the blanket. It is based on the Indian program, which is really a good idea. I mean, this is a nice program, the three-stage program. I mean, this is the best compromise we can find by combining thermal reactors with high conversion ratio and fast breeder reactor. Really very good. Well, this one has been said several times also. Sorry to be a little bit fast, but advantages, melting point, chemical stability. I skip this one, you understand. It has been said once again. Industrial challenges. Mining, roughly speaking, not big challenge, except a little bit more irradiating material you have to manipulate before processing it. The tailings are less a problem than the uranium, waste from mines, because of the Thorium is half-life 1 minute instead of 8 days for radon. But it's a detail, and it's not a big, well, really big issue. Fuel manufacture, I took this one from India. There is an experience. It's possible to fabricate thorium fuel. There's no problem, even at industrial scale. This is the main message from this. Well, the issue of uranium-232, this has been also presented once again, but it's just to remind how uranium-232 is formed. There are 3 different ways from nuclear standpoint to fabricate. But the main problem is here. Thallium-208 is very intensive gamma, very energetic. Don't put in your hand a piece of uranium-233, which is possible, uranium-235, you can take it in your hand, even pure. Don't do this with uranium-233. You will, you know, not die immediately, but it's very highly radioactive. I mean gamma emission, because of not uranium-233 itself, but it is mixed with uranium-232. There is a drawback for this, is for the fabrication of fuel, but it is possible with remote handling system. And there is an advantage for this is for proliferation resistance. I will come back on this point in 5 minutes. Maybe you will be surprised. Reprocessing, you have been told many technical things on this. It's more challenges because of the dissolution is more, but it is feasible. It is another story if you want to make it at the industrial scale. You have to make enough R&D. You know, at the high plant, we make 10 or 20 years of R&D. On the paper, it is relatively easy to dissolve uranium fuel in nitric acid. You put it in a vessel, put nitric acid, put the fuel, it dissolves, and it gives you, at industrial, it gives you a high plant. So when you go to industrial scale, it's a different story. You make a lot of R&D, but it's feasible. As I said, we have reprocessed 30,000 tons of fuel in the Hague with using Purex. Carlo is not here, unfortunately, but he said that Purex is, not good, but it works. As I said, refabrication of uranium-233 bearing fuel is not so easy, but it was made 40 years ago. With the present technology, it's a question of cost, but technically it's not impossible, of course. We have the technology. When you see how MOX fuel are fabricated is behind glove boxes in almost automatic devices. Complicated, but feasible. Waste and non-proliferation. Is it the first time you see this curve? I don't think so. Each presentation you see this curve. It is what we call, in fact, since it's very well-known curve, you have to know here is sievert per gigawatt electric year. It's in French, sorry. It's what we call the radiotoxic inventory. If you eat the waste each morning with your coffee, what's happening? It's happening this. You die if, because it's highly radioactive. So there has been hundreds and hundreds of papers and scenarios on this issue. Roughly speaking, it is true to say that if you have thorium cycled with uranium-233, clearly there are less minor actinides. That's clear. It is simple. It is physics. Because americium, curium, and neptunium are simply produced by plutonium. So if you remove plutonium, you have no more minor actinides, of course, if you have uranium-233. But for that, you have to implement a thorium, uranium-233 cycle, which is not for tomorrow. You have just first to begin with plutonium, at least, and with plutonium to generate minor actinides. Okay, so it is not so simple to say, well, it's a waste-free cycle. That's not true. And anyway, the bulk of the waste are fission products. Yeah? Minor actinides, of course, are important because they are long-lived and alpha emitters. But once again, you generate, at least during first decades of implementing thorium, you generate minor actinides. After that, it's okay, no problem. So here you have an example, just one example of comparison with uranium. This comes from the protactinium-231, but anyway, it's under the natural uranium radioactivity. So after a few tens of thousands of years, this is not an issue because it's very low radioactive. Another question is, I am provocative, is it necessary to separate minor actinides? And some people leave it underground. I mean, it's not a big issue. It's another discussion. We can discuss this also. Proliferation. A gun-type nuclear weapon. I've been involved in this during many years in this area, so nuclear weapons, so I know a little bit on this topic. A gun-type nuclear weapons is feasible. What is a gun type? Do you have just two half sphere of fission material? You do this, and you make an explosion. It was a Hiroshima bomb. Principle is very simple. It is very simple. The problem is to have the fission material. Look at this. It was a test made in 1955 with the nuclear weapons made of uranium-233. Partly. There was a little bit plutonium. I don't enter into design, but mainly the fission material was uranium-233. So don't tell me that it's impossible to make a nuclear weapon with uranium-233. It's proliferation resistant. Okay, I will tell you that. Nobody say that, but when you hear when politicians are, heard that, well, it's waste-free, proliferation resistance. Well, oh my goodness, that's fantastic. This is the answer to your question. All proliferation pathways are not easy to implement, and this should make thorium cycle a little bit more proliferation resistant. There has been here studies, here by Mr. Bruno Pelot, a study on this, on the proliferation resistance of thorium fuel cycle. It was made on the, sorry to say that, but on methodology that I developed myself, which is called SAPRA, a simplified approach for proliferation resistance assessment of nuclear energy system. The method that I developed, you apply this method to assess the proliferation resistance. It was that thick report. Unfortunately, it's not public report because it was ordered by a private company. But anyway, the conclusion of this, depending on the scenario, you can make it more proliferation resistance or less. The problem is, I come back just to this, uranium-232, which makes difficult to handle uranium-233 sphere, which is true, but you can make uranium-233 with very low content of uranium-232. It has been done. American did fabricate 400 kilograms, 400, which is 20 times the critical mass. You can make 20 nuclear weapons with this, with very low content of uranium-232. Very low, 7 ppm instead of 1,000. So you can handle it like this. Don't know. Maybe, yeah, I know, but okay. But it's possible. If you put thorium in, sorry to say that, in thorium in a blanket of fast breeder reactor, you have the very low content of uranium-232. It's like plutonium, weapon-grade plutonium from putting uranium-238 in blanket of fast breeder. So my message here is to be careful of any, very big statement like non-proliferation, waste, and so on. Be careful. It's not so simple. I don't enter into the details of the economy, but I made also some economic. I just want to underline that it is true if you put thorium tomorrow, if you implement in thorium, yeah, okay, that's okay. I will finish in 1 minute, maybe. First, you have already 25,000 tons of thorium available on the world. 9,000 tons is available in France. With this, you can start tens and tens of thorium reactors. Tens and tens of thorium maybe started tomorrow without any mining of thorium. 25,000 tons, okay, and it's already available. So the thorium, once again, is not a problem. Of course, you have not to enrich uranium, so it's an economy. The problem is the back end, which is a little bit more expensive. So you have just one point. The chemical part of a reprocessing, the chemical part, the core of the process in reprocessing plant is only, I would say, 25% of the total cost of reprocessing. All the rest is head-end part, many, dissolving and so on, and treating the waste and vitrification and plutonium management and many things. So if I have the detailed cost of the Hague plant, I can tell you the figures are true, and the chemical part, even its double price to process thorium, it's not a big influence of the reprocessing cost. Okay. Status of the art is being said, well, it is written here. Conclusion, takeaway points. I had 3 or 4 slides of takeaway points. I just skipped it because of time. So my main conclusion is not this one. Well, this one is relatively optimistic. I think thorium cycle presents real attractive feature, really, and it needs to have R&D on this. But do not exaggerate and make thorium a miracle. It is not a miracle. It is an interesting option for the future. I am quite convinced of this. And tomorrow, when it is done today, in this frame, the priority is to develop and qualify a fuel for today's reactors. We have to go progressively. I think there's a future for thorium. I'm quite convinced in this once again. But don't tell every decision makers in the newspaper that thorium is a miracle. It's against that we defend. Because one day they will, you said there is no waste. Well, look at this. There's waste. Non-proliferation, well, we have been told by specialists that sometimes you can make, so wait a minute. So you will be, completely, in French, discredited by when the people, so you have to explain the things. It was done, by the way, I did appreciate very much a presentation from India, which was very realistic, and they have a very good program. This is my feeling. Sorry for that, but I would like to conclude here. Thank you.
So the paper is open for questions and for discussion.
Sorry, maybe I was too. So people say, "Well, you can ask questions. You can discuss."
Don't worry. I think in a good scientific discussion, when it's advocates and when it's also counter advocates. And
there is one here.
Please.
Thank you. How would you include the ADS systems in your story?
Well, it's another. Well, good question. Often, thorium is linked to ADS. Hyde said there's no. You speak about ADS without speaking thorium. I mean, this is another problem. This is a question of reactor technology, the interest or not of EDS. I think it's a good question. I'm not going to discuss here the advantage and the disadvantage there are not. It's an interesting project, but it's not directly linked to. To the topic of thorium. I mean, you can, the past reactor was not ADS. We put thorium in other things than ADS. If there is a good mariage, how do you say that? A good, complementarity between ADS and thorium, it's okay. But, my feeling about, I have my own feeling about ADS, but I don't want to discuss in details here because it's a little bit long. The only thing I would like to say is simply about the cost. I said that I'm not going to say something, but I'm going to say something. Now, once again, when it's claimed everywhere that ADS are very safe. I said that this morning. It's make me very angry. When you have a fission, you have two fission products. Okay. These two fission products release energy, whatever the system is, And this makes the residual power. If there was not this, there would not be Fukushima, TMI, or even, Chernobyl was another problem, but anyway. Everywhere you have still the residual power, even in ADS. For a given amount of energy, one fission is 200 MeV, is neutrons, and is release of residual power. Three things fission, is physics. So you have to remove the residual power. Otherwise, you go to the big accident. That's as simple as this. Of course, you can imagine more or less efficient, as is air-cooled or in ADS, which is a fine idea. But don't tell me that much safer or less safer than that. You can imagine systems, as it was imagined by ADS, air-cooled, natural air cooling systems, or even, which are better. If you say it is safer, you are going to remove the containment? And you are going to go to the safety authority saying, well, I have ultra-safe reactor. I don't need a containment. You know the answer.
Stefano, please. I'm sorry, it's not.
Well, you say that both uranium and thorium could complement each other. In the present days, where uranium-235 exists in big amounts, but the future of thorium is tomorrow, when uranium-235 has to be replaced. So the fight will be then with thorium and uranium-238. So it is in this perspective that the debate has to be
well, once again, absolutely right. You know all the figures today. We have 7 billion tons of uranium. The consumption is about 60,000 tons per year today, so it's 100 tons. It's 100 years or 200 years of uranium. If you stay to this, at the constant nuclear energy level, it's only 1 or 2 centuries of uranium. And after that, go away, for a constant. If you imagine the deployment of nuclear doubling or tripling, of course, there are 2 solutions. Either you find additional reserves of uranium, which is possible. People say there are plenty of uranium. We didn't discover it.
That's possible.
That's possible. It's an option. There will be debate about this. And the second possibility is that we do not discover additional and we develop nuclear energy. In that case, of course, thorium would be an interesting option, except if you develop the fast breeder reactors with plutonium uranium. We come back to my 1 gigawatt electric. 7 million tons of uranium, if it is transformed into plutonium, and if you fission it, you have nuclear energy for 7,000 years. It is true. I mean, it is as simple as this. The equation is not complicated. We have not to make differential, integral, and whatever, actualization, and it is as simple as this.
Yeah, but then thorium has its main advantages in,
yes,
in that case.
Yeah. Well, it is what I said. You know, maybe in competition because of many good characteristic of thorium,
like
physical, maybe less waste in that case because of thorium uranium. And the scenario of India is once again very good. I'm not especially paid by India. But
okay, let's take somebody from India to comment on this.
Well, I think I just want to put something in, what shall I say, in my own perspective. I think it's nobody's case, at least I didn't hear, that thorium has no problems and uranium has all the problems. I think that is not the issue. The issue is there are some unresolved issues with uranium. Now, if the nuclear power has to grow, we have to find answer to those issues. There may be many other alternatives. I thought in the context of this meeting, let's examine whether thorium can help alleviate some of those problems. Now, that may be in the context of a little better proliferation resistance. That may be in the context of easing the recycle, which makes larger energy available, and so on and so forth. Clearly, the days when nuclear energy began, there are several options related to thorium which were not available because the burn-up that one could get in those days was small. Today, even in light water reactors, you can get high enough burn-up to get those advantages out of thorium.
Yeah.
So it's only that comparison and nothing more than that. I thought I'd just mention that.
Fully agree, yeah.
Thank you for
Okay.
these words of wisdom. I almost would like to
There
quote
was
it.
another question, but maybe
There
we have
is
no time.
another question, but there
That
is
was there, yeah.
theoretically the
This
time
is
for
the
questions
last
over,
one.
but
Oh, well.
let's take one more.
Competition between thorium and EU uranium-338. What about fusion? Should we
Oh my goodness.
consider this player?
I take my joker. I take my joker. No, it's not, it's not fusion. Well,
Okay, maybe we
I don't know what to think about.
should
Okay,
stop
okay.
here. Thank our
you.
speaker again, and maybe the public allows me before I call up the next speaker to make the small comment that such a critical talk was, of course, or is by most of us, highly appreciated because it's necessary to make the arguments and the counter-arguments. Now, there's only one thing which I would like to point out because I understood a little bit Dominique Greneche telling us some of the community are very naive or are very, that might be true. But I would like to insist that in all European projects, whatever, ADS, whatever, Thorium, never ever any of those projects has forgotten in its safety analysis that the residual heat is the underlying problem. So there was, at least at the level of these European projects sponsored by the Commission, never any